Hello to everyone and welcome to a new Energy Capital interview. Today, I'm very happy to have the opportunity to talk with Brent Constantz, CEO of BluePlanet. Brent will talk with us about BluePlanet CCUS technology, which compared with similar technologies, can convert carbon captured into manufactured aggregates. In this sense, this technology can provide customers with positive economics and sustainable solutions. Brent, it's very nice to see you today. How are you?
Good. Thanks for having me.
Thank you very much, Brent. So I'll start with our first question. In your experience, Brent, what are some of the challenges that companies currently need to overcome while looking for CCUS technology solutions?
Well, it's really financing the first plant. I think people want to see a operating, commercially successful operation as you go through. But the indication is that there's really quite a bit of financing out there once the technology risk is removed. Our first plant that we're building here on San Francisco Bay, we were able to finance completely with debt because it looks like the favorable economics will carry that pretty well. So, and I think it's probably the right test because there's a lot of things you can do with carbon besides inject it into the ground. And I think some of them may have broader potential to really impact CO2 and climate change than others. And I think that's the level of differentiation you'll see is the ability to get plants financed that will have positive ROIs for investors.
So in this regard, Brent, what would you recommend to CCUS providers in terms of technology development to keep up with the need to reduce the amount of CO2 emissions?
Well, humans are responsible for about 40 gigatons of CO2, 40 billion tons of CO2. And most models indicate that we need to mitigate 10 or 20 billion tons a year to really have hope of maintaining our environment the way it is. And that's really a lot. You got to remember in 1 gigaton, there are 1,000 megatons. And, sometimes the numbers are overwhelming to people, but we really need to mitigate at least 10 or 20 gigatons a year, which is a lot. If you hear about a project that's sequestering 100 megatons, 100 million tons of CO2, that sounds like a huge project. But in fact, it's inconsequential with respect to climate change. Even 500 million tons, it's only half a gigaton. And so I guess my advice to people wanting to go into this space to affect climate change, at least, is, if it's not a solution that if fully successful could mitigate gigaton levels of CO2, it's not that it's not a worthwhile cause, but it does not have the potential to really affect the planet for our grandchildren in any way. And we should focus on the things that have massive potential in the ability to at least take a gigaton of CO2 out of the system. And the other aspect is permanence. A lot of the work on CCUS are things that are just temporary waste stations for the CO2. And it's going to be reintroduced to the atmosphere after 5, 10, 20, 30 years, when our grandchildren are around. And that's not really helping anything. So unless it's the best way to make the product is to use CO2, if that's the best way to make biofuel, great, make it that way. But if you're just going to make it into biofuel and then combust it and re-emit it, I'm not sure that's really helping things.
And could you tell us more about BluePlanet's CCUS technologies, which convert carbon captured into manufactured aggregates?
If you look at the distribution of carbon on Earth, over 98% of it is in limestone. And limestone is the most used rock in concrete. And it's about 70% of all concrete. And there's over 50 gigatons of rock mined every year. So what BluePlanet does is we mimic processes where deposits like the White Cliffs of Dover or the Great Barrier Reef are formed, which are biomineralization processes to make that calcium carbonate. And we're able to do it in minutes. And we can capture CO2 from any source, regardless of the concentration. So something that makes BluePlanet stand out amongst any company in this space is at no point do we ever try and concentrate CO2 or turn it into a liquid to transport it or handle it. We simply do what happens to 99% of all the carbon on Earth. We diffuse it into water and form carbonate and make calcium carbonate out of it. So we don't undergo the capital or operating costs associated or carbon footprint with concentrating CO2, because point sources of CO2 like power plants or industrial plants are putting out different concentrations of CO2. None of them are putting out pure CO2. So BluePlanet can handle any of those concentrations and capture it and turn it into limestone, which is a marketable product. And it works into the existing infrastructure of the world. For example, here in the state of California, we use about 240 million tons of rock every year in our projects. And if that rock is, say, limestone, I would need 105 million tons of CO2 to make 240 million tons of rock. And the state of California has the Global Warming Solution Act, which says by 2030, we have to get from 400 million tons output of CO2 a year to 300 million tons output every year by 2030. And we could reach that whole objective just by the state of California specifying BluePlanet limestone for its projects, which it's already spending money on, instead of importing aggregate from British Columbia or Mexico or the 100 miles away Sierra foothills, which is what we're doing now. And the reason that's important is that BluePlanet isn't dependent on any sort of subsidy or carbon price or anything like that. It's just a standalone, profitable operation that in countries that can't afford subsidies, which is 95% of the world, they'll be able to finance this with just the same money they're already spending on rock, even in the poorest countries of the world, all without a subsidy.
Following that last part of the answer, Brent, in what ways do these aggregates provide companies with positive economics compared to other CCUS technologies?
You know, in any construction project, concrete is a major part of the project. And, having if the goals, like if you're Microsoft, for example, and you've set the goal that you're going to capture all the CO2 you put in the atmosphere since 1976, or you've declared that your whole company is going to be carbon neutral by 2030, and you're building huge data centers with giant concrete slabs that have huge carbon footprints, or you're looking to mitigate CO2, this is perhaps one of your only avenues. A lot of companies have come out and set goals for mitigation of CO2, but in most cases, there's no way for them to access that. They're going to buy credits, but there's actually be more credits than there is actual CO2 getting mitigated. So, and there's this other issue of permanence. Mineralization is actually one of the only really permanent forms of sequestration of CO2. Even geologic sequestration has to be monitored to look for the leakage of the CO2 that's been injected underground. But once CO2 is mineralized into limestone, the White Cliffs of Dover have been there 100 million years, and it's not going anywhere. So it's offering a really different alternative.
So besides from the financial benefits, the economic benefits, and also the environmental benefits, what could be other benefits, maybe socially, of this particular CCUS technology through aggregates, for instance, for urbanization?
I think it really goes to the fact that you don't have to be in a rich country to do this. Japan, North America, Europe, a couple other places have huge subsidies that allow some of these technologies like CCS, geologic sequestration to exist, but they wouldn't exist without those subsidies. And, we have to look at the majority of the world. How are they going to address CO2? It shouldn't just be a privilege for rich countries. It should be accessible to all countries. And all countries are procuring rock. And all countries have this immense power of procurement. The construction industry is the largest industry. And this problem is too big for governments. And it's too big for governments to pay people not to pollute. There's way too much CO2 to do that. And so by accessing a methodology where the poorest country in the world, by procuring their rock for their projects, could also be mitigating CO2 is a huge benefit. But there are other interesting benefits. For example, the rock we make is limestone. All limestone is the skeletal remains of marine organisms. And there's an adaptation in the crystals that we make, because they're similar to like a lobster, that makes them highly reflective. And so there's an interest in the global urban heat island of urban centers, where the temperature, because of all the dark surfaces, gets much warmer. And so the air going into the air conditioners is already very hot, and there's a lot of energy wasted. And BluePlanet aggregate, when it goes in concrete, increases the albedo dramatically and makes for a cool surface. And in the future, in the next decade, you're going to see cool surfaces in urban centers are one of the major factors for the urbanization in cities. You're going to see roads, parking lots, roofs, siding, all are going to be high albedo surfaces. And because we mimic nature, the shells, we can also make colors and still have them be highly reflective. And it's the Lawrence Berkeley National Labs, where the National Urban Heat Island Center is, has received major DOE funding just to look at the albedo and reflectivity of the BluePlanet materials for incorporation in all aspects of urban life.
And well, finally, from your experience, what kind of industrial users could leverage CCUS technologies and particularly aggregates?
Anyone emitting CO2. We're not dependent on any particular concentration or temperature. We're not afraid of the other pollutants, the criteria pollutants, like sulfur dioxide. That turns into sulfate and goes into the limestone. The NOx compounds, many of the transition and heavy metals that we're worried about actually go into the limestone in an insoluble form and are permanently sequestered there. Cement plants, steel mills, alumina refineries, oil refineries, ethanol refineries, natural gas-fired power plants, coal-fired power plants, blue hydrogen from steam methane reforming, and actually the atmosphere itself. There's companies out there doing direct air capture now, but they're all trying to get the CO2 to 100%, to 1 million parts per million, and then looking for something to do with the CO2 once they get it there. And it turns out there's nothing to do with it. There's already companies like Air Liquide and Praxair and Air Products that have been selling CO2 for decades, and it's a saturated market. And it's a huge waste of energy to try and put all that energy to concentrate it to a pure form, when the only thing you can really do with it is have the government subsidize you to inject it underground and monitor it. So we don't do that. We can take it directly out of the air and convert it directly into carbonate and make it into mineral, even from the air.
Well, Brent, thank you very much for sharing all this information and insights with us. I don't know, do you want to add your final take on this?
Yeah, I think if you look at the Earth and you look at where the CO2 is, and if we look at the atmosphere of the Earth, It's an envelope of gases about 80,000 feet thick around the planet. It's got about 750 gigatons of carbon in it. If you look at the whole hydrosphere, all the oceans, lakes, rivers, ice caps, it's got about 38,000 gigatons of carbon in it. If you look at the whole biosphere, all the rainforests, all the plankton in the oceans, there's about 5,000 gigatons of carbon. But if you look in the lithosphere, in the form of limestone, not coal or other things, just limestone, there's about 50 million gigatons of carbon. And when you see a distribution pattern like that in nature, what it tells you is that's the lowest energy route, and that's why all the carbon is in limestone. And the way to deal with the global carbon problem is just put a fraction of a percent of that 700 gigatons in the atmosphere back into the lithosphere, where it'll stay forever. And it's clearly the path to follow.